Okay, so I shall be giving a brief intro to massive gravity, as the title suggests. So I'm not going to spend too much time on this conversation. I'm hopefully going to sort of get across, if you like, some of the philosophy of how we think about massive gravity theories and in general sort of effective field theories. Which some of this philosophy is slightly different than the GR mentality, and so I'll sort of explain as I'm going along a little bit the language and how we think about things. But so to some extent, what this talk, as some of the other talks in this in the school are about, is, you know, are there any other theories beyond general relativity, beyond Einstein's theory? And so typically when we talk about that, we tend to those types of things fall, if you like, into two categories: high energy modifications, UV modifications, and low energy modifications, or large distance modifications, IR modifications. So for UV modifications, the story is more familiar because people have been thinking about it for a while. So we all expect new physics to come in at the Planck scale just because of quantum gravity effects, but it may be even lower than that. You may have some grand unified theory where new physics comes in below that, or string theory where physics comes in at the string scale, or you may have large extra dimensions or even small extra dimensions where you expect new physics to come in at the scale of the Kaluza-Klein modes. All those examples are what we call UV modifications in modern language. So they modify high energy physics, but not the low energy physics. And so from the point of view of the low energy observer, you can basically summarize all of them within the language of effective field theory, as long as the UV modifications preserve Lorentz invariance, at least. And in the language of effective field theory, essentially these modifications can be described by adding to the low energy action for GR, higher curvature operators. So for example, even just from the curvature, we can construct things like Riemann squared, Riemann cubed, Riemann squared, box Riemann squared, etc. All these higher order operators. There's a bit of back reaction there. Is that okay? By construction, or by the language of effective field theory, all these extra operators should be treated as small perturbative corrections to the leading low energy parts, which is just the Einstein Hilbert action plus the possible cosmological constant. And so this is pretty well understood, how to think about ultraviolet modifications to general relativity. What is less familiar is the opposite, which is the infrared modifications, where you actually really modify gravity at large distances. And so these, when we talk about modified gravity, in fact, this is usually what we have in mind, because we're really changing gravity at the scales that we can detect, if not solar system, certainly cosmological scales. And the principal reason for thinking about these and why people have introduced them is cosmological, primarily motivated by, or at least recently, the discovery of cosmic acceleration, and so coming up with alternatives to dark energy, or indeed just trying to tackle the cosmological constant problem from a new point of view. So I won't talk too much today, at least, about the cosmology of these classes of theories. I'll mainly be discussing the formalism today, but that's the sort of motivation in the back of the mind of why we even talk about IO modifications. And there's another sort of more pragmatic perspective, which is that it's nice if we want to put constraints on general relativity, which particularly in the modern context of, with all the information we've got from gravitational waves now coming in, we'd really like to know, you know, is Einstein's theory of relativity correct, even at low energies? And it helps to have alternatives to test against, just in the way if we want to, say, do precision tests of, a nice example I always like to give is if you want to do precision tests of the superposition principle in quantum mechanics. So we take it for granted that quantum mechanics is linear in the sense it preserves the superposition principle because it's described by fundamentally by states in a Hilbert space. To test that experimentally, you need to have some notion of what would happen if you violated that. And for example, that's the motivations why Weinberg developed his nonlinear version of quantum mechanics, was to precisely test that linearity. So similarly, it's nice to have alternatives to general relativity in order to test general relativity. Now, the guiding principle as far as this talk is concerned is to think, if we're thinking about modifications to general relativity, it's helpful to understand what makes general relativity special. And the perspective, the emphasis, which is important for that, is why is general relativity special, is that it is the unique local and Lorentz invariant theory describing an interacting single massless spin-2 particle that couples to matter. I'm going to talk about this in a bit more detail and give more, in fact, more of the argument than is often given in talks, at least, because it's sort of crucial to building up and going beyond that. And these ideas go back, in fact, to many people. I think Gupta was the first one, and then Feynman emphasized it, and people like Weinberg, Dazer Walders also added parts of this story. And so the guiding principle is, so general relativity, what it does respect is locality, the local theory. It's Lorentz invariant in a precise sense, and in terms of degrees of freedom, it describes degrees of freedom of a massless spin-2 particle. And it is the unique theory that does that, unique up to the cosmological constant term. And so once you recognize that, you say, well, if I'm going to go beyond general relativity, I have to change one of these assumptions. For example, you could imagine breaking locality, but that's rather severe change, so I don't want to do that. You could imagine breaking Lorentz invariance. That's also severe, not as severe as breaking Lorentz invariance as locality, but I'm not going to do that here. Now, what most people do is then, when we're talking about modified gravity theories, is that the assumption they break is that there is just a single spin-2 as the only degree of freedom. They don't necessarily assume there's other spin-2 degrees of freedom, but they may assume there's, say, other spin-0 degrees of freedom. So the most famous examples of modified gravity theories, such as Brand-Sticky, FFR, and so on, all introduce additional scalar modes, in other words, spin-0 particles, which may or may not be light, so effectively massless. But I'm going to, for this talk, we'll take that to be true. We may give up that assumption, but perhaps more crucially for this talk, we're also going to give up the massless assumption. And that is quite non-trivial in itself. This is a slide. So in fact, this slide here is from 2008 from a summer school I gave with Claudia Duran, of different sort of alternatives to dark energy models. And already then there was quite a lot of structure, but this was sort of pre-massive gravity. And so once you recognize you've got massive gravity, there's all sorts of extensions of that, so multi-gravity models, and these tie into, as I'll discuss hopefully today, into Galilean theories and their generalizations and so on Mondesky models and dust and so on. They're all sort of connected and borrowing different ideas from each other. I'm going to introduce some of these ideas today. Okay, so let's go back to general relativity again and take in a bit more what makes it so special. So there's lots of nice things about general relativity. So probably most importantly is its symmetry. It's a diffeomorphism invariant theory. That's just a fancy word for saying that it exhibits four local symmetries, which are general coordinate transformations. So I can change my coordinate system any old how I want, and I should not fundamentally change the physics. I may change the way I describe the physics, but I'm not actually changing the physics. And so the laws of physics should be independent of our choice of coordinate system. Now you can actually write any theory in a way in which it has this symmetry. So it's really sort of crucial in that there is a third coordinate system in the problem in the absence of matter. So that's what makes general relativity true. You can use so when I said you can make any theory invariant on coordinate transformations, you can do that by the so-called Stuckelberg procedure, which I'll get to later. But in general, if you have to do the Stuckelberg procedure in order to make it invariant in the coordinate transformations, then it means that there is fundamentally a preferred frame. In general relativity, there is no preferred frame. So it's manifestly invariant under general coordinate transformations, or what I should just call diffeomorphisms from now on. Of course, in general relativity, because of that emphasizes the notion of geometry, and so gravity is described by the curvature of space-time. Standard cartoon story, the curvature is proportional to the stress energy momenta tensor. So you all know that, I'm sure. It also has other nice features. So it's also locally Lorentz invariant. And so in some sense, this is about the equivalence principle. And it's an important point because every metric is locally flat. If we can go to a local, if I'm thinking about a space-time whose signature is minus plus plus plus, so it really is a space-time, one time in 3 space directions, then locally I can go to a coordinate system where it's locally Minkowski plus small corrections. So for example, around some point in space-time xp, I can change coordinates so that the metric around that point has a Taylor expansion, where the first term in that Taylor expansion is the Minkowski metric. The linear term is 0. I can choose coordinates always so that's true. That's the Christoffel symbols vanishing. And then the next order term comes in a quadratic order in the departure, with the coefficient being the Riemann curvature at that point. So that's essentially what's describing a locally inertial coordinate system, the system in which you don't, at leading order, you don't think you're in a gravitational field. You think you're in flat space. Of course, if you go far enough away from that point, you start to recognize you're in a curved space-time, and that how far you have to go is given roughly by 1 over the square root of the curvature. So it's the curvature radius. Now that local Lorentz invariance is important because sometimes when we're going to think about general relativity as somehow perturbative around Minkowski space, and so sometimes people say, well, black holes are not perturbative around Minkowski space. A black hole is a big perturbation. But that's actually not true locally, because even for a black hole, essentially everywhere within a black hole space-time, for example, at the horizon of a black hole, I can always, at a given point, locally go to a coordinate system where it looks like Minkowski, and the corrections are small around that. Indeed, as is well known, the actual curvature at the horizon of a black hole is typically quite small. So if you're sitting there, you don't actually notice too much. It's only when you actually get to the singularity, which is where anyway the space-time breaks down, where that is not true. But of course, singularities in some sense are not real. They're just a reflection of a breakdown of general relativity. Now, the last crucial point, and this is the one that we're going to sort of pick up on even more so, is that, which I've already mentioned, is that general relativity is the unique theory of a massless spin 2 particle. A point of view which which goes back, well, many authors, but Feynman in particular emphasized it, and Weinberg and Dazer and so on emphasized the arguments into that. And that's, of course, a crucial argument within the context of string theory. So the fact that when you quantize a string, you get a massless spin 2 state is one of the arguments to say that it should ultimately describe a quantum theory of gravity. So as I say, in fact, Feynman has a nice book on this story about how you get gravity from thinking about things. Gravity as the description of interacting massless spin 2 particle. And this basically sort of borrows very much the concepts of how we can think about Maxwell's theory as unique theory describing a massless spin 1 particle. And again, as I say, I'm going to emphasize this argument because it'll be important to understand how to go away from it. But it's useful to recognize that we'll see that, in fact, diffeomorphism invariance in this picture is, if you like, a derived concept. And the equivalence principle is also a derived concept. And indeed, there's a nice paper by Weinberg in which he argues why the equivalence principle has to come about from this sort of, from basically just trying to write down an S matrix for graviton scattering. I'm not going to go that far, but I'm going to emphasize why the diff symmetry plays an important role. So just to remind you, general relativity, of course, is described by the Einstein-Hilbert action. And the crucial fact is that there are only two gravitational modes. There are only two propagating degrees of freedom in general relativity. The two tensor modes, or two helicity 2 modes, depending on your language, which pictorially looks something like that. And that sort of paradox is a crucial part of the story, because we describe a spin 2 particle by, in Lorentz invariant language, we have to describe it by a 10-component symmetric tensor. And yet there are only two gravitational waves. So there's this huge, massive redundancy in general relativity. We're supposed to be describing a theory of only two propagating degrees of freedom, but the building blocks that we're given is a metric with 10 components. So 8 of those components are not physical in some sense. They're not propagating. Maybe not physical is maybe an exaggeration, but they're not independent. They're determined in terms of really the two physical propagating degrees of freedom in some way. And so when we write down a theory of an interacting massless spin 2 particle, we need to remove those 8 degrees of freedom inside the 10-component symmetric tensor, the 10-component h mu nu. And to remove those 8 degrees of freedom, the way we do that is introduce 4 gauge symmetries. Now we only need 4, not 8, because when we have a gauge symmetry, every gauge symmetry in the language of Dirac constraint analysis is associated with what's called a first-class constraint. So it removes a degree of freedom because there is a constraint associated with it. That constraint is the generator of that gauge symmetry. But it also removes another degree of freedom because there is a gauge symmetry, and therefore I can choose a gauge. So when I have 4 gauge symmetries, I can remove 4 degrees of freedom just by a gauge choice, and the other 4 are removed by the constraint associated with that gauge choice. So that removes a total of 8 degrees of freedom, giving me 10 minus 8 is equal to 2. So in other words, if I want to construct an interacting theory for a massless spin 2 field, which my starting object is 10, I need to introduce 4 gauge symmetries. Now again, we're doing this in the context of fundamentally Lorentz invariant theory. So those 4 gauge symmetries, well, what can they be? They can either be a single vector's worth of symmetries or 4 scalar symmetries. But there's only 2 distinct possible scalar symmetries that you get for a spin 2 field. Is one where you shift it either by something proportional to the metric, or you shift it by d mu d nu times a scalar. So there aren't enough scalar symmetries to solve the problem. So the unique symmetry at the linear level that you can have that will do the job is something which is determined by a vector, which I've called here psi nu. So I have a vector's worth of gauge symmetries. But my basic object is a tensor, so I need to construct, I need to have a gauge symmetry for my tensor, which is built out of a vector, otherwise, so there's only 4 of them, and therefore I need something with another index, and the only thing I've got around is essentially the derivative. And then by symmetry, this has to be symmetric and the mu nu, and so essentially there's a unique possibility for what the gauge symmetry is, which is where I shift, the linear level that is, where I shift h mu nu by something goes like d mu psi nu plus du psi mu. This is all we could do for a massless spin 2 theory in 4 dimensions. Now this symmetry, which is correctly called the linear diffeomorphism symmetry, anticipating where we're going, but it's really just a U1 symmetry, analogous to Maxwell, and it's sometimes called spin 2 gauge invariance, because it's really just the spin 2 analog of Maxwell's gauge invariance, where you shift a mu goes to a mu plus chi. So the crucial difference now is that the gauge parameter is itself a Lorentz vector. It has an index nu, and also there's 2 pieces here because it has to be symmetrized. So that should look familiar, but maybe just the order that could have come to it is different. So, and then you can say, well, how would I construct a free theory, a free interactive, that makes no sense, a free theory of a mass for spin 2 field. And so I want something that looks like a kinetic term. So something with a box. But whatever that kinetic term has to respect this linear diffeomorphism symmetry, aka spin 2 gauge invariance. And so you can write down every term you get. If you make the assumption that the action has only 2 derivatives, then there is a unique kinetic term. And sometimes it's written in the language of the so-called Lichnerowitz operator. But for our purposes, it's actually more useful to recognize that it's equivalent to this less familiar, strangely, I've never seen this in a general relativity book, but even though it should be there. But the quadratic action can be written in this so-called double epsilon form, where I've introduced the Levi-Civita symbol. So epsilon ABCD is that object which is equal to +1 or -1 or 0, depending if it's fully antisymmetric. So epsilon 0, 1, 2, 3 in 4 space-time dimensions is +1. And then it's completely antisymmetric in their interchange of any indices. So if there's any repeated index, so for example, epsilon 0, 0, 1, 2 is equal to 0, and epsilon 0, 1, 3, 2, which is just where I've interchanged one of them, will be -1. So there's the Levi-Civita symbols. So it turns out the unique quadratic term in the action, which has only 2 derivatives, is equal to this one, where this is the Lorentz metric here, which is needed only to sort of pair up the indices. And just to see why this is the case, so don't worry about the overall normalization of the action, that's just a convention. But let's consider how that quadratic action varies under a gauge transformation. So if I do the variation of the action, I get 2 pieces, one from a variation of this, one from the variation of that. But I can also integrate by parts at will. So it turns out that those 2 pieces I get are just the same, because the one from variation of this has 2 derivatives on it. The one where I vary this doesn't have 2 derivatives, but I can integrate by parts and put these derivatives back onto that. And so we get 2 terms which are identical when I do the variation. That looks like this. And we know our gauge symmetry is such that I've changed the, this should be in the psi thing here, but anyway, this under a gauge transformation, the spin 2 perturbation transforms like this, the symmetrized version of this combination. And again, if I plug that in, I just get 2 identical terms, so it gives an overall 4, with now 3 derivatives acting on chi, after I've done a bit of integration by parts. But the crucial thing is, because there's 3 derivatives here, then I have to repeat at least one pair of indices from the same Levi-Civita symbol. So in this case, little c and little d come from the same Levi-Civita symbol here, but this is antisymmetric with respect to that, whereas this is symmetric, obviously, because derivatives commute. And if you have antisymmetric times symmetric, it automatically gives you 0. So the kinetic term for a mass of spin 2 field is uniquely fixed in terms of this double epsilon structure. And you see that the double epsilon structure, the antisymmetry of the double epsilon structure, is the crucial thing to see why it's gauge invariant. Again, this is not something that's emphasized in GR books, but it's nice. You'll see it's important later within our story. Okay, so we're building up slowly. So now we want to think about the nonlinear theory. So that's a free theory, but we really want to think about interacting theory. Now, when we go to an interacting theory, it's nonlinear. It may be that the gauge symmetry itself also picks up nonlinear pieces. So we have to think about what are the nonlinear completions of the linear spin 2 gauge symmetry. So remember, the guiding principle is the same. We still want to keep 4 gauge symmetries. So the degree of freedom counting is 10 minus 8 is equal to 2. But the gauge symmetry itself could admit nonlinear extensions. So for example, so we want to do this in a way that preserves Lorentz invariance, but you can start to imagine, well, how, you just write it down from brute force. What else can I add into this? I can add things like, h squared and h cubed and so on. I have to make some assumption of how many derivatives I do. If I start adding more derivatives, it gets more complicated. But whatever I write down has to be Lorentz invariant. It has to preserve the symmetry of h mu nu. And there's all sorts of things in principle I could write down within the gauge transformation. But crucially, the freedom of our gauge symmetry is fixed by the fact that it forms a group. So if I do one gauge transformation and then I do another gauge transformation, that has to be equal to a single combined gauge transformation. And that in practice translates into something about the commutator of the transformation generators. And this is where basically where all the hard work is, and I'm skipping over the details because otherwise I'd just be talking about that. But the punchline of all these arguments, and the most complete proof there's a nice paper by Wall that gives probably most detailed argument of this, but it's implicit in the work of Deza and so on, is that there are only two nonlinear extensions of the spin-2 gauge symmetry, at least if we make an assumption on the overall number of derivatives in the gauge parameter. And the two are the trivial one, which is this: we don't change the gauge symmetry, we just keep the symmetry to be linear diffeomorphisms all the way up. And then the other one is full diffeomorphism symmetry. So this is just the linearized version of this symmetry, which you may or may not recognize is just a particular way to write a diffeomorphism symmetry. When you write the metric as an Minkowski metric plus h mu nu, this repackages into the form for a diffeomorphism. So the key point, and this is really what the key argument is in all these uniqueness theorems, the key point is that at the level of the symmetry, not at the level of the action, equations, and motion, or whatever, it's really at the level of the symmetry. At the level of the symmetry, there are only two nonlinear completions of the spin-2 gauge symmetry, which is crucial to have to describe a massless spin-2 particle. And that's why there are only two types of interacting theory describing a massive spin-2 particle, although one of them is largely trivial, and so you probably never heard of it. And so the punchline is when you just take the notion that you have a spin-2 particle, a massless spin-2 particle, because it's massless, it needs a gauge symmetry, and then you ask that there is a nonlinear gauge symmetry, then you're uniquely led to that nonlinear gauge symmetry being diffeomorphism invariance, and the spin-2 particle being automatically part of a quantity that we recognize to be a metric, and therefore you're led to geometry. Because once you have a metric and diffeomorphism invariance, then you're automatically talking about geometric formulation locally. Now, as I say, though, we still have two options. Where the two options diverge is when you start to couple. If I just take the trivial option where I don't make the symmetry nonlinear, so I have h mu goes to h mu plus blah blah blah. Now let's think about coupling to an external source, which is reflecting matter. So I'll call that source J mu nu. Could have called it T mu nu, but I pointed not to call it T mu nu for reasons become clear. So let me call that source J mu nu. That because of the gauge symmetry that you need to describe a massless theory, that symmetry has to be preserved when we couple to matter. Otherwise, we run back to the same problems that will have additional degrees of freedom. So the matter coupling itself has to preserve that symmetry. So if we just try a coupling like this, a linear coupling to the source, and ask how does that change under coordinate transformation, under the spin-2 gauge transformation, then this shifts by something like that. And the only way that this can be zero, so that the symmetry is preserved, is if the current here, the J mu nu, is identically conserved. Notice I said identically conserved. That's a crucial fact. And that's why it can't be the stress energy of matter. So we can't couple, and this is the argument that's sort of nicely gone through in Feynman's book. It can't be the stress energy, because although the stress energy of a matter is conserved in Minkowski space, it's conserved by virtue of its equations of motion. And when you couple to the spin-2 field, the equations of motion are modified by the coupling, and therefore the original thing you call the stress energy is no longer conserved. And so because the conservation is not an identity, then you have to then add in higher order terms in order to try and correct that failure for the stress energy to conserve. And adding in those higher order terms, you're inevitably led to the linear spin-2 gauge symmetry not being the right one, and you have to go to the full diffeomorphism symmetry. However, if we do have a source which is identically served without using the equations of motion, then there is an interacting theory. And there are such theories. We don't tend to talk about them, but they sort of implicitly play a role later on. So I can write down sources which are identically conserved using the same trick. If I write down a double epsilon structure with 3 tensors here, and I take combinations of those tensors to be either 2 derivatives of a scalar or just the metric itself, then these combinations are identically conserved, because if I differentiate them so to mu, well, the Lorentz metric is just a constant, so that drops out. And this thing, when I put a differential in, I get the same argument as before. I'll have 3 derivatives acting on a scalar, but the 3 derivatives will, 2 of those indices has to come from the same Levi-Civita symbol, which is antisymmetric, but the derivative is symmetric, so it'll be automatically 0. So I give this particular example is interesting because it shows up exactly in the so-called decoupling limit of massive gravity, as I'll get. So there do exist, in some sense, interacting theories for master spin-2 fields in which you just have the linear gauge symmetry, but they're not gravitational theories, so the source could not be the stress energy. Now, what all the standard arguments show is that as soon as you actually couple to matter, because of the reasons I said, because the stress energy conservation can no longer hold as an identity, it has to hold through the equations of motion, and so you need to add in extra corrections to preserve that. You're always led to the fact that the only symmetry which can describe a truly gravitational theory is full diffeomorphism symmetry. So by the uniqueness theorem, that is the only symmetry we have, at least up to a certain number of ordered derivatives. And so that is why we're uniquely led to a covariant theory, or theory of a metric coupled to matter with diffeomorphism symmetry, which of course is what general relativity is. Just a few comments on the kinetic terms. In the first case, where you just have linear gauge symmetry, it turns out that there is another option. Well, so the kinetic term is still unique. Because we've already discussed why that's unique, so that's just this double epsilon structure. But obviously in the full nonlinear case, we have to have a nonlinear version of that structure. So it shouldn't be just invariant under linear spin-2, it should be invariant under the full diffeomorphism symmetry. And there's a unique term, and nowadays we recognize it as more or less a trivial thing. We know that the action has to be covariant, invariant, so the Lagrangian has to transform covariantly, so it has to be built out of the Riemann scalars from the Riemann tensor. So if we restrict ourselves to saying the action is only 2 derivative order, the only option is the Ricci scalar itself, and that's what leads us to general relativity, up to, of course, the cosmological constant piece, which is a sort of trivial correction in this story. Okay, so finally, that's a long intro, but intentionally long because we're going to use many of those ideas again. We get to what happens when we think about the spin-2 field. How do the arguments go? So one argument says, well, as soon as I make a theory massive, I break the gauge symmetry. I don't need gauge symmetry anymore. So diffeomorphism invariance, for example, is broken, or the linear spin-2 gauge invariance is broken. And so if I don't have the symmetry, surely I could do anything then. I can write down any old thing. There's all sorts of operators I can write down in that case. And so I lose any kind of nice organizational structure. Now, fortunately, that isn't true. And in fact, even in the case of a massive theory, the underlying masslessness the symmetry that would be there in the massless case still plays a role in the organizational structure of a massive theory in a non-trivial way. And indeed it has to, as we'll see, because if we just naively start writing down any old operator we can that breaks gauge symmetry, in general what we'll find is that we'll find too many degrees of freedom in the case of massive spin 2, some of which turn out to be ghost and highly unstable. Avoiding that is essentially one of the key issues. And it's really the underlying symmetry of the massless theory that does that. And so the point here is that now for a massive theory, we need spin 2 in Lorentz invariance in 4 dimensions. Spin 2 particle should have 5 degrees of freedom because it's just 2s plus 1. The naive quantum mechanics thing you learn in quantum mechanics, where you have 2s plus 1 states for a particle of spin s equals 2, so that's equal to 5. So there should be 5 types of gravitational waves for a massive theory. It's Lorentz invariant. And so ultimately we need to have a theory describing 5 degrees of freedom. But again, we're starting with a metric which has 10 components. Spin 2 particle which has spin 2 commands. So we need to somehow find a way to get rid of 5 of them. Now, a toy example to understand really what the difference between the massless and massive and why the massless symmetry is still important. A good example is to look at the Proca theory, which is just the theory of a massive spin 1 particle in so-called unitary gauge. So in which you just take Maxwell Lagrangian, which obviously describes a massless spin 1 particle, and you just add a mass term and you break the gauge symmetry. You just accept it. And that's called the Proca action. Now, so let's think about this as a sort of toy version of the spin 2 case. And it is in many ways a toy version of the spin 2 case. It captures many of the key features, not all of them, but many of them. So in particular, let's put this Lagrangian in canonical form. So I introduce the momenta conjugate. This is still a Lagrangian. So if I integrate out the momenta and get back to this action, so this is not equal to this. It's more that this, when I integrate out pi I, which is the momenta conjugate to ai, I get back to that form. So this is an equivalent form of the Lagrangian, a so-called canonical or phase space, or sometimes first order form of the Lagrangian, where I have a momenta pi I, which is conjugate to ai. So I have the time derivative ai here. And they have, this is the kinetic term and the p squared term, if you like. The magnetic field comes in as just like a potential term, so I, j indices are only running over the spatial parts. And that's what I have for Maxwell. And then this is my mass term. That's just a first order form for the action. Now, so what's the difference between the massless and the massive case? It's really about the role of A0. So A0 is the 0 component of the 4 vector. In the massless case, you see that the phase space Lagrangian is linear in A0, and therefore A0 is a Lagrange multiplier for a constraint. That constraint is that the di pi I is equal to 0. That's called Gauss's law. And that constraint is the so-called first-class constraint. So in that case, the constraint itself is the generator of the underlying gauge symmetry that, of course, you already know that Maxwell's theory has. So you knew that that had to be the case. You knew that Maxwell's theory is gauge invariant. And so when you write any gauge theory in the Dirac phase-space formalism, then the gauge symmetry must be generated by a so-called first-class constraint in Dirac's language. And there it is. It's just generated by A0. First-class constraints are one-to-one with gauge symmetries. In the massive case, that's completely changed. The mass term, being quadratic, automatically breaks the linearity of the action in A0, and therefore A0 is no longer a Lagrange multiplier. It's still non-dynamical. There is no A0 dots in the action, anywhere. So it's a non-dynamical or auxiliary degree of freedom. I could actually integrate it out. I could solve for A0. I get A0 goes like di pi I over m squared and plug it back in, and I generate a funny di pi squared over m to the 4 interaction. I could do that. But if I don't do that, and I sort of say, think of A0 as a degree of freedom, it is a degree of freedom, but it's not a degree of freedom, it's non-dynamical. And so that one way to say that is that the momenta conjugate to A0, which is what you get by varying the Lagrange respect to the time derivative of A0, is actually 0. There is no momenta conjugate. And so you could view that itself as a constraint, but it's an example of a so-called second-class constraint, a constraint that is not in itself associated with a gauge symmetry. So sort of less significant constraint. Now, in the Lorentz invariant theory, second-class constraints come in pairs. So once you recognize one, another one will automatically follow, at least as they come in pairs. But it turns out that in the massive Proca theory, you have two second-class constraints. Whereas in the massless theory, there's one first-class constraint. So the counting in the massless degree theory goes as follows. I have 6 phase-space variables ai and pi I. So that's 6. And I have a first-class symmetry, so I can drop from the constraint and the associated gauge symmetry. I lose 2 from that, so it's 6 minus 2, which is 4, and 4 is 2 times 2, and that's why there's 2 propagating degrees of freedom for spin 1 particle. In the massive case, I view it slightly differently. So I could say, well, AI and A0 together as 4 variables. Naively, I have then 8 phase space degrees of freedom. However, I have the constraint that one of the pi's is 0, an associated second one from that. So I lose 2 degrees of freedom from 2 second-class constraints. So I get 8 minus 2, which is 6, which is 2 times 3. And that gives me my 3 degrees of freedom for a massive spin 1 particle. So it all works out exactly correctly. So there is a sort of equivalent description. Whenever I have a pair of second-class constraints, I could also view it as having come from a gauge symmetry. So the number of degrees of freedom I lose from 2 second-class constraints is the same as the number of degrees of freedom I lose from 1 first-class constraint, 1 gauge symmetry. And so that suggests there's another formalism for the problem whereby I introduce gauge symmetry and rewrite those second-class constraints as first-class ones associated with the gauge symmetry. And that is the famous Stuckelberg formalism, which I've already hinted at already, that plays a crucial role in understanding these theories. So Stuckelberg, of course, was interested in a massive spin 1 particle. What he recognized is if you take the Proca action and you just perform a gauge transformation and then promote the gauge parameter to a dynamical field, we now call the Stuckelberg field chi. So chi is actually a field here, it's not a gauge parameter. Then you recover a gauge symmetry, because now it's clear if I take that action, I can then shift a mu by d mu times a gauge parameter and shift the Stuckelberg field by the compensating gauge transformation in the opposite direction. And then this term will now automatically be gauge invariant, because this will cancel, the minus sign from this will cancel the plus sign from that, and this anyway is gauge invariant. And now the counting is very simple. Now I just say, well, what I have is Maxwell coupled to a scalar, and therefore, because this is Maxwell and because everything's gauge invariant, I'm going to get 2 degrees of freedom from the Maxwell field, a mu, and 1 from the scalar, and that gives me my 3 total degrees of freedom, and that's trivializing, but that's what you get from the Dirac constraint analysis for this particular system. So by taking what we would now call the unitary gauge Proca action, where there's no gauge symmetry, and undoing the unitary gauge fixing, so unitary gauge is basically just the gauge in which chi is equal to 0. So if I now say chi is not equal to 0, so I make that a field, Stuckelberg field, so that now I genuinely have a gauge symmetry, then I can count degrees of freedom as I would count for a massless theory. So even though we're dealing with a massive spin 1 particle, the counting of degrees of freedom is the one determined by how the massless theory works because I've introduced the gauge symmetries that a master's theory would have. Now, this is more than just a trick. It turns out that this really sort of captures in various limits the correct effective degrees of freedom, the correct effective, the dynamics of the system. And indeed in many effective theories, where so-called Goldstone formulation, Goldstone is just the global version of the Stuckelberg fields, and sometimes it's the names are used interchangeably. The effective theory for Goldstone modes for various broken systems in which symmetry is effectively broken, what capture essentially all the interesting dynamics of that system. Just to give you an example of why this mentality is useful, let's think about a bad situation, which is where we'd said, so okay, I want to write down a mass of spin 1. I know the gauge symmetry is broken. So why for the kinetic term do I add? Why do I just look at f mu squared? Why don't I add something like d mu a mu squared? Well, the reason I don't do that is because this would lead to 4 degrees of freedom, because A0 is no longer non-dynamical. There's now a D0 A0, so an A0 now is no longer dynamical, and there's no second-class constraint associated with the vanishing of its momenta. Now, this is also easier to understand in the Stuckelberg picture, because if I now perform the Stuckelberg trick, I do a gauge transformation, promote the gauge parameter to a field, then the action for this is now obviously higher derivative, because I have box chi squared. And so that gives the equation for chi. Now I think of that as a degree of freedom. Obviously has higher derivatives in its equation of motion. And so by the Ostrogradsky argument, that will lead to ghosts, additional degrees of freedom. And so the degrees of freedom counting this problem will end up being the 2 for Maxwell, the 1 for chi, but then there's also 1 Ostrogradsky ghost associated with chi because it has a box squared type action. And so I have 4 degrees of freedom, which is 1 more than I should do for a massive spin 1 field. So again, let's to the spin 2 case, and the general principle is the same. So if you got that from how we did it from the Proca, it's the same thing. So even though a massive spin 2 particle will break the underlying gauge symmetry, it's nevertheless the case that we need to preserve some of that structure from that underlying gauge symmetry. So for example, although we no longer have first-class constraints, we still need to have second-class constraints in order to remove the initial necessary degrees of freedom. Alternatively, if we think about it in the Stuckelberg picture, we still need to demand that the equations of motion for the Stuckelberg do not have Ostrogradsky intervals, so they're not higher derivative. That's another way of thinking about it. Okay, so let's do that then. Okay, so let's think about again, I'll just think about the case 1 case where we have linear spin 2 gauge symmetry because it's much simpler. We perform the Stuckelberg trick. And so we now what we're doing, this is a gauge transformation. This, on the other hand, is the Stuckelberg replacement. We replace h mu nu everywhere by h mu nu plus d mu chi nu, blah, 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 where chi now is supposed to be a dynamical Stuckelberg field. It's not a gauge parameter. And you can easily see that there is a unique quadratic mass term for which is acceptable, which doesn't give high derivatives for chi. And it's the so-called Fierce-Pauli mass term. And then again, I've intentionally written this in this double epsilon structure, where this is the Lorentz metric and these are the 2 h's. And you can see why this is the right structure. And again, it all relies on the same argument. So if I look at the part, if I plug in here, the part which comes from, which is quadratic in chi, so I'm going to have an h squared, h d chi pieces and d chi squared pieces. So look at the part which is quadratic in chi. Up to factors, this will give things like this. And after I integrate by parts a bit and put the indices together, I can put it in a form where the derivative acting on chi is coming from the same index of the same Levi-Civita symbol here. Now the Levi-Civita symbols are antisymmetric, so that means that this projects out the antisymmetric part of that derivative. And that's, of course, is how you define a field strength, like d mu chi nu minus d nu chi mu. So if I now take a normalization where I say that the Stuckelberg field chi goes like 1 over m times a vector, you'll get two 1 over m's which cancel the m squared in the mass term, and then this turns out up to a factor to give f mu squared. So it's exactly the correct kinetic term for a massless spin 1 particle. So the fact that that worked is only because I chose this double epsilon structure. And that's why the Fierz-Pauli term is unique, because of this. Of course, it's not the way Fierz-Pauli stated it, nor argued it, I should say. But in terms of modern understanding, this is the quickest way to recognize that the Fierz-Pauli structure is crucial. But antisymmetry of these epsilons here is crucial for repackaging this quantity into a field strength to recognize this as the kinetic term for spin 1 field. The cross term, the piece linear in chi, if I now, so I do that change, chi goes to 1 over ma, this gives something that isn't automatically gauge invariant under U1. So obviously the f mu squared here, that's got a U1 gauge invariance, separate from the spin 2 gauge invariance, and now sort of generate a U1 gauge invariance. But this term breaks that. So it's helpful to then do a second Stuckelberg trick on the helicity 1 mode, where I also introduce a U1 Stuckelberg, where I replace a mu now goes to a mu plus d mu pi, like a gauge transformation parameter. And I do that with a 1 over m here to cancel that m. And then pi here is the so-called helicity 0 mode. And that mixing term, that last mixing term then gives you something like this. So the m's dropped out by a normalization. And if you integrate this by parts, you recognize that this is actually pi times ddh, double epsilon, which is essentially the Riemann tensor, which is gauge invariant. And this mixing term can actually be removed by so-called demixing transformation, where I shift h mu goes to pi to mu nu to get rid of that. And then after that, you just generate something that goes like pi dd pi, and it generates a kinetic term for pi, and you recognize pi as just the helicity 0 mode in the problem. So I won't actually do that step because I don't need to, but the key point is that pi is the helicity 0 mode, a mu is the helicity 1 mode, and h is the helicity 2 mode. So to summarize, the unique quadratic Lagrangian, the so-called Fierz-Pauli Lagrangian, is most conveniently written in this double epsilon structure. I've suppressed the indices here, but the indices are contracted in pairs, where you have the unique quadratic, so it's not unique actually, so it's the unique quadratic gauge invariant kinetic term, and the unique mass term for which you don't generate higher derivatives when you plug it in. There's no Ostrogatsky ghosts. And in the process of showing that, we perform two Stuckelbergs. So we shift h mu by the gauge parameter with a 1 over m normalization. And then we do another Stuckelberg on the U1 part to introduce explicitly the helicity 0 mode. And that brings out another m. Now, this procedure is crucial, again, to all the phenomenology of these kinds of theories, because as we make m small, we go in the massless limit, this piece gets big relative to that, but this piece gets even bigger. And so what we'll see is in the limit in which the mass is small, the dynamics of the helicity 0 mode pi completely dominate. And that's a crucial part of the story. And the simple reason for that is just this normalization. We needed to put an m squared here in order to cancel, ultimately to cancel the m squared sitting there. So it's just fixed by the canonical normalization that comes from the mass term. But it has a crucial effect. It means that this thing will dominate as m goes to 0. Just a side comment, in the case 1, the spin 2 gauge symmetry, it turns out there is an interesting, at cubic order, there is a kinetic term, which is 2 derivative, but has cubic orders in H, which also just comes from this double epsilon structure, which was recognized in these papers. And so there is the kinetic term for the mass, in the case where you have linear diff symmetry, is not unique. Well, there's 2 terms, allowed terms. In the full case, the nonlinear case, there is no equivalent of that. The unique term is the Einstein-Hilbert term again. And there's turns out to be there's unique mass terms, which the argument I'll get to. Okay. Okay, so now we sort of really get to the punchline. So I've sort of given you some of the arguments leading up to massive gravity, and I'm not quite there yet. I'm going to take a step back and just give a little bit of the sort of prehistory and talk about soft and hard massive gravity. What do I mean by that? So in general, when we think about massive theories of gravity, there are soft theories where there is not an actual pole state in the propagator. There's no actual spin-2 propagating pole in the propagator. Rather, there's an effective resonance state, a spin-2 resonance state, which is an unstable particle. So technically, it's, for those that know about these things, it's a pole on the second Riemann sheet, but it's an unstable particle. So that it's not a hard state. And that unstable particle shows up in a spectral representation of the propagator for a spin-2 particle as a peak in the spectral density. So here what I've written is effectively the effective scattering amplitude between two sources. If you're not familiar with that language, let me just sort of explain a little bit. So hopefully you are familiar with the concept of a generating function in quantum field theory. So the generating function, you take the action, the path integral, and you add a source term, and you integrate over the field, and that defines the so-called connected generating function. If you do that for a free scalar field, what you get, if you allow me to write invert box minus m squared, the generating function for a free scalar field, the connected two-point function, is something quadratic in the sources with a 1 over box minus m squared. Now, 1 over box minus m squared is a non-local operator, but if I wrote it in momenta space, it becomes local. And so the generating function in momenta space between two, the Fourier transform of the two sources just has this form. So this, what you recognize here is the Feynman propagator sandwiched between two sources. So for free theory, the generating function is quadratic and just describes a source and then a Feynman propagator between them and then a source. So it's diagrammatically, you're just drawing a single propagating connected line with two sources at the end. Now in interacting theory, when you add in interactions, W of J is not quadratic, it has all sorts of orders. But if you just look at the quadratic part, this structure at quadratic level gets generalized into something that looks like a sum over three Feynman propagators, but where there is a spectral sum. So the mass, the hard pole mass, is replaced in general by a distribution of masses, where the mass squareds are mu, and there's some distribution of that. That distribution may be pure continuum, or it may have some pole parts and then a continuous part. So when I'm writing this formula, this complicated formula, that's what I'm writing. It's essentially the generating functional between two external sources from exchanging an effectively interacting spin-2 field. And so that can have various pieces. It can have a massless spin-2 pole, where you have the polarization structure, which is that for a massless spin-2 particle here, between two stress energies in the Fourier distribution of the stress energies. You can have massive spin-2 particles. In that case, we call the theory a hard mass gravity theory because there's an actual definite pole. Or you can just have a continuum of massive contributions, but there's no actual pole. In that case, we call it a soft massive gravity theory because there's no actual asymptotic massive spin-2 state, but you get a resonant-like state or a stable spin-2 particle. So historically, the first explicit example of a soft massive gravity theory was the so-called DGP model, in which you get exactly this kind of structure. The interaction between two stress energies is pure continuum. There's no pole bar, it's pure continuum. And the way this is obtained is that, you had an infinite extra dimension. So it was a 5-dimensional theory in which you lived on the brain. So the stress energy we're talking about is living on the brain here, but there's an actual extra dimension. And gravity in the extra dimension is massless, but from the point of view of the effective observer on the brain, it looks like a resonant state, because obviously Kaluza-Klein modes in the extra dimension look like massive states on the brain, but because the extra dimension was infinite, those Kaluza-Klein modes were a continuum, not rather than the original Kaluza-Klein picture of a tower of modes. You have a continuum of states. And by adding a localized kinetic term on the brain, so the action was 5dGr plus 4dGr, by adding that extra 4d part, they were able to localize the resonance, rho of mu, well, sort of, it's not very sharply localized, but effectively localized to create a theory for which in 4 dimensions looks like a soft massive theory with a resonance. And the dynamics of this is in, say, 5 dimensions, the Newtonian potential will go like 1 over r squared. 4 dimensions, obviously 1 over r. So the way this theory worked is that at high energies, it looked 4-dimensional. You got 1 over r behavior. Low energies, you'd look 5-dimensional. You got 1 over r squared. And if you tracked the spectral density, its form was such that the effective propagator, effective Feynman propagator, had an effective k-dependent mass, which went like square root of minus k squared, such that in the UV, where k is large, the mass is irrelevant, and so it just looks like k squared. It looks like my k squared minus epsilon, which is that for a massless theory. So at high energies, it looked like 4D gravity, whereas in the IR, this part dominated, and so it looked like a 5-dimensional theory in the IR, and so you got a modified theory of gravity at large distances. Okay, so now I come to hard massive gravity. So again, just to give you a bit more about the Stuckelberg field and what the logic is here, you know, in an ideal world, we have some kind of Higgs description of what's going on. So if you think about in the Higgs mechanism for breaking a symmetry, the Stuckelberg field is essentially the, well, if you think about it, sort of abelian-Higgs model, just as a toy model for the Higgs. In the abelian-Higgs model, as a toy model, then the Stuckelberg field is exactly the phase of the Higgs field. So it's that object, which this should be pi here, beg your pardon, pi goes to pi plus chi. Is that part of the field which shifts linearly under the gauge transformation? So when you do an abelian-Higgs, for the abelian-Higgs, we do a gauge transformation. The pi here, which should be the pi, I don't know why I wrote rho, shifts by chi. So that is the thing that is the Stuckelberg field. On the other hand, the Higgs boson in that language is the perturbation of the modulus around the VEV for the field. So when the Higgs boson is very massive in the abelian-Higgs model, we can integrate it out, and the effective dynamics is determined by the massless Stuckelberg field, or sometimes called the Goldstone mode. What's crucial in this story is the symmetry breaking pattern. So obviously in the standard model, it's this symmetry breaking pattern that's important. So for us, what is the symmetry breaking pattern? Well, in massive gravity, if you talk about a hard mass gravity theory, then you're breaking essentially the full diffeomorphism symmetry down to just the Poincare symmetry. So technically, we need to introduce an external global symmetry and break that down to the diagonal subgroup. But roughly speaking, what you're doing is you're taking massless theory has full diffeomorphism symmetry, whereas you make it massive, all you've got left is just the Poincare symmetry, or the Lorentz part is the crucial part. Similarly, if you have a bigravity theory, it's often mistakenly said that bigravity, for example, is diff-invariant. But, well, that's true, but it's in a trivial sense. The crucial part is that it still breaks the diff symmetry. So what it does is it takes theory with 2 copies of diff symmetry, breaks it down to a diagonal diff symmetry. So it's the same amount of symmetry getting broken in massive gravity theories or bigravity theories. So in that sense, they're both equally bad, depending on your perspective, or equally good. So when we do a Higgs for gravity, unfortunately, we don't have a Higgs mechanism. So I should say, we don't know a Higgs formulation for gravity. There's been some claims of having constructed one, but in reality, there isn't one for Lorentz invariant massive gravity. You can do it for Lorentz violating mass of gravity, but not for Lorentz invariant mass of gravity. But we do have a so-called Stuckelberg formalism, which is what describes the low energy effective theory in which you integrate out the bosons. And so here we're borrowing basically from full nonlinear diffs, the Stuckelberg procedure that we did before. It's a little bit different though because of the symmetry. So let's imagine we've got two metrics now, and you can think of one of the metrics. So we have to have two metrics in the mass of gravity theory. So one is going to be the dynamical metric, and the other one is what you call the reference metric. But if you like, you can think of the reference metric as the vacuum expectation value of some operator which is spin 2. And so it's like the VEV of the Higgs field. So it's not weird, in that sense, it's not weird that we do have a reference metric, but all it is like when we have the Higgs theory and then we look at the effective theory in a broken state around some vacuum expectation value of the Higgs field, then the Higgs VEV will be sitting there in every formula because of what we're doing. So similarly here, because we're looking at the effective theory in the broken state, the VEV for the spin 2 field, whatever it is that's breaking the diff symmetry, is going to sit there explicitly. We'll call that VEV for the spin 2 field the reference metric, and conventionally it's usually represented by FB nu. Now what the Stuckelberg procedure recognizes is once you have a reference metric that breaks diff symmetry, because a fixed reference metric is not invariant under diffeomorphisms, right? It's because if it's just got explicit numbers like 3, 2, 6, 8, and I do a coordinate transformation, it's no longer 3, 2, 6, 8. So the reference metric is what's breaking the diff symmetry in the same way that the VEV of the Higgs field breaks the gauge symmetry for what the Higgs is breaking. The Stuckelberg procedure says, okay, I'll do a gauge transformation on that object. And in this case, it corresponds to replacing the reference metric by its gauge transform version. Well, you know how to do a gauge transformation for full diff symmetry. I just do a coordinate transformation where I have new coordinates, which I've called phi a here. And then I promote those new coordinates to dynamical fields. That's the Stuckelberg procedure. That's the first step. But we can use our knowledge of what happens in the linear theory, which will partly be borrowed by the nonlinear theory. And that is that we know that in order to do the full Stuckelberg analysis, not only do we need to introduce a vector, we'll also need to introduce a scalar, which is the Licity 0 mode. And the normalization of that, there'll be a 1 over m in the vector. We saw that before. Now, because we're doing gravity, there's an m Planck in front of everything. So it's to get the canonical normalization, you need to do m Planck. But in comparison to the previous discussion, the crucial thing is here you have a 1 over m. And in the derivative of pi, you have a 1 over m squared. That's what we understood before. And when, in the gravity case, that's an m squared m Planck. And so it packages together in this scale lambda, sometimes we usually call lambda 3, which is a geometric mean between the Planck mass and the mass of the spin 2 field. So it's closer to little m than it is to the Planck mass, but it's intermediate between m and m Planck. So we do that decomposition like before, and we do this decomposition on the reference metric. Now the crucial thing is, turns out to be discovering how to square root. And the reason that's as follows is, as I said before, in the small m limit, clearly it's the Licity 0 mode that dominates because it has a 1 over m squared. So if I compute f, and I just set the vector part to 0 for simplicity for a second, it turns out that the f then, just because of this structure, in the limit m goes to 0, in particular if you scale m Planck to infinity in such a way that this lambda scale is kept finite, the vector drops out, and this thing turns out to be this structure, which ends up being a complete square. So this is 1 plus 2 pi plus pi squared schematically. And therefore, if you take this square root combination, you get something that's linear in the double derivatives of pi. So this square root combination of the inverse metric times the reference metric is special because it is linear in the double derivatives of the Listy zero mode. This is the only object that's linear in decoupling limit in the double derivatives of the Listy zero mode. Well, why is that important? Well, the Listy zero mode, as I say, dominates the interactions for small m. It comes in this particular combination where it's got two derivatives of pi on it. And there is an accidental, and it is accidental in this formalism, symmetry, which is called the Galilean symmetry, which had been recognized earlier from DGP days. But here in the massive gravity context, it's explicit, the significance of the Galilean symmetry, because obviously if we shift pi by a constant plus something that's linear in x mu, when I act two derivatives on that pi, this object is left invariant. So the way the Listy zero mode comes in massive gravity, it automatically builds this Galilean symmetry. Now, as I say, let me skip that actually. So the Galilean, actually, skip that because of time. So the Galilean symmetry, it had been first recognized in the decoupling limit of the DGP model, but here it becomes out explicitly. In the Galilean, there are a special set of Galilean interactions which are well known, which I've written in a particular form here, which is useful for us. So the so-called Galilean operators, they're written in this double epsilon form. I've suppressed all the contractions, but where you have pi without any indices, so pi is a scalar, Lorentz scalar. You have two epsilons and three etas, two derivatives of pi. That's something that's quadratic in pi with two derivatives. Once you do all the actions, this is just pi box pi. So that's just the kinetic term for a massless scalar. So that's one, if you like, the Galilean operators. This is special because this Lagrangian, although it's not invariant under the Galilean symmetry, because there's pi without two derivatives on, the action is invariant. It shifts by a total derivative, and so the action is invariant. So all these operators here are special in that their action is invariant under the Galilean symmetry, although Lagrangian is not explicitly invariant. You can generalize this to now non-trivial interactions as a so-called cubic Galilean operator, which is where you take two dd pi's, two etas, and contract with the double epsilon. So this would be ABCD, ABCD, AA, BB, CC, DD, sorry, and then pi just sitting out front. This is equivalent to the operator box pi d pi squared, the so-called cubic Galilean operator, which was first discovered, if you like, in the context of the decoupling limit of the DGP model. But then there's other stuff. There's the so-called quartic Galilean operator, where you do now dd pi cubed times eta pi, and the quintic Galilean operator where you just have four dd pi's contracted with the double epsilons, and then a pi sitting out front. So those operators are well known in game theory, special. Now, they're also less well known, but at least those of us outside of the massive gravity community that are less well known, but within massive gravity well known, is there are also special interactions between the Galilean and elasticity 2 field, H mu nu, which preserve linear spin-2 gauge invariance. And those are built in the same structure. So I take H, which is a tensor, and I take the four combinations I need to contract, eta, dd, pi, h. In fact, this is the term that already came from the Fitz-Pauli mass term doing the decoupling limit analysis, which I've already given you this. This term is gauge invariant under spin-2 gauge invariant, because if I shift this by d chi, or d psi, I can integrate the derivative by parts. I get three derivatives here, but then this is 0 because one of the derivatives has to be repeated. Repeated indices from the epsilon, so it's 0 by antisymmetry. And you can go up. There are also other interactions, h dd pi, h dd pi, and that's as far as you can go for interactions that preserve second-order equations of motion between an elasticity 2 field and the Galilean. These interactions, this double epsilon structure is sometimes referred to as characteristic polynomials, because it's what you get. Obviously, double epsilon defines a determinant. Definition of determinant has two epsilons, and so it's what you get by expanding a determinant. If I take the determinant of h plus dd pi plus eta and expand it to linear order in h, all the possible terms I can get superpositions of this term, and this term. These are sometimes referred to as characteristic polynomials. So that brings us back to square root structure. So once you recognize that in the so-called decoupling limit or small mass limit, the square root of this metric in this combination is the object that's linear in dd pi. And once you recognize that the only allowed interactions for a Galilean and a Helicity 2 field which preserve second-order equations of motion are these ones, you put those two things together and you're led to a unique hard mass theory for gravity in 4 dimensions, or this generalizes to any number of dimensions, in which the mass terms are exactly these characteristic polynomials, or these double epsilon structure, built out of this square root combination, square root of g minus 1 f. So indeed, if you go back to unitary gauge, and just send f back to little f, so unitary gauge is setting a and pi to 0, so phi a is xa, then capital F is little f. Then in unitary gauge, this combination, square root, if you just take the mass term to be the determinant, the characteristic polynomials you get by expanding the determinant in the mass term, then you guarantee that the decoupling limit of this action exactly gives these interactions, which are known to be those unique interactions which give second-order equations of motion, and therefore don't introduce any Ostrogaussian ghosts, and therefore maintain the overall number of degrees of freedom. So that's how it was recognized that this was the unique theory for massive gravity. It was unique mass terms, and indeed since then we argued, I mentioned it earlier, that in fact the Einstein-Hilbert term is the unique kinetic term as well. So even though a massive theory breaks diffeomorphism symmetry, nevertheless demanding the overall structure that it preserves only propagating 5 degrees of freedom restricts it down to a relatively unique theory for a hard mass gravity theory. Now, I'm getting to the point I should probably stop and ask for questions because I've got lots more to do, but I'm going to carry that on tomorrow. But let me see, I can just mention that this story easily generalizes to bigravity. So in bigravity, as I say, you're breaking, overall you're breaking, you do have a diagonal copy of diffeomorphism invariance in the theory that gives you the impression of its covariance. But the point is that you have 2 metrics to start with, 2 dynamical metrics. So the massless theory of those 2 metrics would have 2 copies of diffeomorphism symmetry. So what happens in a bigravity theory, what the effective theory for the breaking symmetry is that you break those 2 copies of diffeomorphism symmetry down to a single diagonal diffeomorphism symmetry. But you can undo that by the same Stuckelberg procedure. Now, however, very interestingly, it's ambiguous how you do that. So you could Stuckelberg, because both metrics are dynamical now, you can either choose to Stuckelberg the F metric, like that, or you can Stuckelberg the G metric. So so there's 2 inequivalent Stuckelberg procedures. Well, no, inequivalent's the wrong word. They're 2 equivalent Stuckelberg procedures, but that look superficially different. So one way you introduce the Stuckelberg fields on the F metric, the other one where you introduce it on the G metric, and yet these must ultimately capture the same physics. And so that means that there is a dual formulation between the 2, which is something called Galilean duality, which I'm not going to have time to get to today, but hopefully I'll mention tomorrow. So in the bigravity formulation of mass gravity, which was first written down by Hassan Rosen, you do exactly the same thing. You write down, I'm going to stop in a second, you write down the now an Einstein-Hilbert kinetic term for G and F in the same mass term. And this turns out to be equivalently the unique interacting theory describing a massless spin 2 coupled to a massive spin 2. And particularly the coupling limit of that just gives you massive gravity. So I've run out of time for today, so I'm going to end there for questions.
That's right.
Carry on this discussion tomorrow.
Perfect.